So I'm in the meteorology department at Reading.
Ready, please, we're starting.
And I'm an urban meteorologist, so probably more on the urban than the satellite part, but the thermal remote sensing is an important part of urban environments, which you've seen already today on multiple talks, but also no doubt in the previous one. Okay. So I've got a set of references. I want to draw your attention to two documents. One I'm going to use is a great textbook called Urban Climates, and there's a WMO document that you can download for free that is on urban heat islands, so that may be relevant. But this has all the references that I'm going to talk about, and you can see this again later on. So what I want to talk about is two things. One is the challenges of the urban environment, and then specifically about the applications. And the reason why I'm talking about the challenges first is I think it's quite important to think about how are we going to deal with some of the problems? What are the things that we need to think about? And then how does that relevant for a particular application? And therefore, how we always have to make assumptions in any research we do or any decisions we're making, but thinking about what the implications of those are, and are those so important that we need to approach it a different way, or do we just need to make people aware of what the implications are of the assumptions? And what I'm going to start with then is, what is the scale of the urban form? Is there any way we can get rid of that thing at the top?
Fine. I have an idea, but I'm not entirely sure.
Okay, because I went with.
You might be able to grab it and
just want to stop showing that. Yes. Okay.
Brilliant. Thank you.
And now, please.
Thank you very much. Okay. So what I want to start with is thinking about the scale of the urban form and thinking about how we view it and its variability. So what we're looking at here on the left-hand side is the facets. So that means things like walls, and you can see that in the walls we have windows, and there is things like air conditioners, and there's the roof and the ground. And then we go up to things such as buildings, and those very if you're sort of small area residential, as we come into central city, those buildings become much larger. They can be multi-storied or single-storied. There's a whole variety. A very critical aspect to urban meteorology is the street canyon, and that's something that we use a lot in numerical weather prediction when we're thinking about how should we simplify the urban area. So in the same way in a forest or cropland, you may simplify it to a plant. The urban canyon, so sort of the street and the buildings and the roof are an important part. When we start to build up from that, then we have lots of buildings with streets, and we see city blocks. Those can be sort of have pretty similar characteristics. Those blocks come together to create neighborhoods. These now are at the sort of scales that are large relative to the buildings. We can see the presence of roofs, but we can't pick out all the details. And then obviously we have the city relative to its surroundings, and that's sort of familiar in terms of things like the urban heat island, where we're interested in what does the urban area look like relative to its surroundings. And those surroundings could be ocean, they could be agriculture, forestry. So why does that matter? So if we're thinking about applications, then people are making decisions at all of these scales. If you are working at your own house, you might decide what color do you want to paint your door. That is changing the albedo, it's changing the emissivity. You may make decisions at the whole building scale in terms of building it. Your planning decisions may start to have an impact at the building scale. They're going to be at the street scale, neighborhood scale. We have implications in planning that go on at neighbourhood scale. So somewhere like London would have, 33 boroughs. They're all got separate, different planning decisions, and then they come out to Greater London. And then we have the city, and the city is normally can be quite important economically in a country, and so there's implications of that. And yet we've just seen COP, and we see that there are global implications. So there are decisions being made by various people at all of these different scales, and they're going to change everything that we might actually make decisions about in terms of other decisions. The large scale are being impacted by these small scales, but they're also in terms of how do we deal with health, planning, energy use, and things like that in the city? Why do people want to know about variations in the city? Why would they be using LST in the city? Is we're going to be for a lot of other impacts. And so we've got to keep all of these together. But decisions are being made at every single one of those scales. So if we think about now the scale of what's going on in a city and what do we see from a satellite. So I've just chosen sort of two scales, something that has relatively rapid return. So maybe less than an hour, maybe every 15 minutes, we might get some information. And if it's clear, we could see the city. So of that, and say again, sort of the London scale, maybe the order of 4 to 5 kilometres. So London would be covered in the order of 100 pixels, whereas if we're looking at something of the order of 100 metres, so the order of, say, Landsat, that may be that we have 10,000 pixels covering London, but we would only see that sort of every 14 days or so. And obviously, if we come down to the facet scale, we're going to have literally tens of thousands of facets within one individual pixel. And even once we come down to the Landsat scale, the sort of high resolution repeated, we're going to be seeing the order of 10 facets. We're going to have multiple buildings even within one grid. So it's really hard to get the information that we want at the right scale for many applications. And we've got to be thinking about how do we play these things off. And we need to then think very carefully about what is the right scale for the question you're trying to address. What do we need to see about that environment, and what are the implications of what we're seeing and what we're not seeing? So that means that we need to think about what are we actually seeing within the urban environment. So probably the simplest case is nadir, we're looking straight down. And so that means that we're going to see the roofs of the building. So for the next wee while, I've simplified buildings to cubes, as urban meteorologists are tending to do. And I'll show you that we even sometimes make it even simpler than that. If we go off nadir, then what we can do is start to see some walls. And depending on the spacings of those buildings, what we make, so we see on the plan view, or nadir, we see the roofs. If we go to an oblique view, depending on how tall the buildings are and what the spacing is, you may see that some walls. It's going to depend on the exact geometry. You'll notice in this case and in the previous case, you've only seen walls from a certain direction. You haven't seen the walls on the other side. So that means that we've got a bias there. With the oblique, we can see with tall buildings, we can see down, but we're not seeing all of the walls. The hemispherical view, which is, for example, a long wave radiometer, we can get a hemispherical view. We're seeing, if we're high, we see now multiple orientations of the wall, but we would have to be very high to see multiple buildings. We're actually only seeing a small number of buildings, but we have seen different directions. So we're always trading off then what are we actually seeing, but we're always, unless we're nadir, we're seeing some fraction of the walls. We're very unlikely to see all of the walls. So we start to think about what is the city. So we often think about the city as being either having aligned cubes or staggered. So you can see that they're offset. That's very important for something like wind flow. We can start to be quote unquote, more realistic and randomly assign the buildings. We start to be more realistic again and have random height. The random orientations sort of allowing the architects to have more fun. And then we move towards something realistic, which you still probably don't recognize your house in that case where you live. I mean, in the sense of, so then we go to something more complicated. And so here we have the sort of random cubes. These three here are all have the same physical properties. They have the same mean building height. They have the same plane area fraction. So if you were describing it in terms of modeling parameters or characterizing the area, you would end up with the same characteristics for all of those. We're getting more realistic by putting trees in here. The difference between level of detail 1 and level of detail 2 is whether we're actually having vegetation present and what the shape of the roofs are. So this is a very detailed model. You can start to pick up some of the characteristics of the facets. You can see, the presence of windows. You can see a different roof structure. This is actually an area of central London, and that is the model of that. And you see, so you saw a lot of detail, but as soon as I take away that model, which is actually very improved relative to those cubes, you can see that it's way more complicated than that. There's lots of different materials, lots of different geometries, and although the sort of more complete model is more realistic, you can immediately see what you haven't got. And that's what people are really living in. That's what the decisions are going to be made about, your individual door or window. Do you clean the windows? All those various things are happening in thousands of different places, even in this one image. So we have to think about urban materials. And I'm going to go back now to some simple urban forms and just think about what are sort of classical materials. So as I said, I started off with cubes, and I actually, for this talk, and I actually realized that is more complicated than what we use traditionally for modeling. What we use traditionally for modeling is a canyon. So this has a roof, a wall, a street, and traditionally, and from sort of numerical weather prediction and climate modeling, the street has no orientation. We assume that there is equal probability that it's in any direction within a weather grid, so that it's randomly distributed. So that means there's no sunny side or no shaded side, and that what becomes critical is what is the spacing of that. So what is the height to width? So here we have a building, and we're seeing one case, this long canyon. This is a physical hardware model. It's in China, and that these are 34 meters across. And in the first case, the edges are 0.5 meters by 0.5 meters, and they're separated in the first case by 1 meter, and then the height to width. So this is height to width ratio of 0.5, and then the second case is a height to width ratio of 2. So basically what they've done is put another canyon in there, and we'll just have a look now at what the implications of that are. So to look at what the surface temperature is in this case, so we've got basically identical geometry and identical materials for the whole area. So the roof and the walls and the ground are similar, and they've used thermocouples, so they've attached them in a lot of different places, and we can get some idea of what the spatial variability of temperature is. And we've got that back again. Okay. So if we look at the red line, that is the ground temperature. So we're looking now at a height to width ratio of 2. So that means that now the streets and the ground it's very narrow. So there's very little space here. Thank you. Okay. Hover.
Okay. Let's try that. Thank you.
Thank you.
Here's the mouse. No. Oh, excellent. Thank you. Thanks so much.
Okay, great, good team effort. Okay, so if we're looking, so the difference in these plots is, whether there's clear skies or cloudy skies, and that what you can see, the ones in the green box are the surface temperatures. So the red line is the ground, and you'll see in all of these cases that the ground temperature has a relatively low diurnal pattern, but on the clear day, the dotted line is the, you can see that that has a large diurnal variation. So the roof has the largest variation. And so if you had just a nadir view and the ground, you would have the contrast then between the looking at the roof, that would be hot, and the ground, because it's very narrow area and shaded, would be much cooler. And you can see that that varies with different conditions. As I said,
I've heard some things, I broke some things.
I can use the mouse. Okay. So now we're actually going to the more complicated situation of having cubes. And so what we have here is, again, this is now a model that's in Japan, and these are 1.5 meter cubes, and they're basically 1-to-1. But now we have more ground, and that we have more complex radiation geometry because we now have more sunlit and shaded parts to the model. And for meteorology, in terms of wind flow, this is a much more complicated situation than if we just have canyons. So the cubes, in the simple way we can sort of identify, you can look at this and all of, every one of you is happy to say where the sunlit and the shaded part of the model is. But as soon as we go to numerical modeling and thinking about high resolution modeling and how those surface temperatures are going to change, we need to figure out which roof is which. So what we did is we sent, this is Will Morrison, who did his PhD and then a postdoc with me. We did with Simona Coathouse, had 2 thermal cameras, and we were looking at these cubes. And that what we can see then is we can pick out where the hottest temperature is. You can see that there is variability within that. And if we look at that through a day, what we see is so we've got time through the day on the x-axis, and this is brightness, temperature. So the materials in this case are all the same. And what we see is that the largest temperature variation is actually in the ground, and that's coming about because of the shading, and that the roof temperature that we can see, this blue, has the highest temperature, and that we have greater variability in temperature during in the morning than what we do in the afternoon. Things become more consistent. Okay, so originally we put out 7 thermal cameras here in central London, and we tried to figure out what was going on in detail in the surface temperature. We then took the thermal cameras to Japan to try and figure out how do we actually think about all this variation that was going on within the materials. Where is the roof? I mean, there are a lot of things that you can see by eye, but trying to build these very sophisticated models to be able to use models such as DART to do radiative transfer modeling to try and understand what was being seen for different field of views is quite challenging. But what we can do by having, in this case, 6 thermal cameras, is that we can see, so we're looking down at the surface, and you can pick out by eye the hottest temperatures that now you're expecting those to be the roofs. You can see that there's differences in different aspects of the ground. So those are all being taken at exactly the same time, and that you can see that you can pick out what must be grass surfaces and what must be, you can see where trees are, you can see potentially different materials being present. These 2 films, the one at the top is going faster than the one at the bottom, but we're looking at the same day. We're looking at this case here. You can pick up, if you look in this area, you can see differences in terms of the materials, in terms of how those roofs are heating and cooling. You can also pick up in this area that can you see my mouse? No. Okay.
Yes. No.
Okay. So if you you can pick up that there is different orientations of the same materials and things like that. You can see the walls, you can see the differences in the windows and things like that. So, and even in this very small area, there's a very large difference in materials that have to be taken into account. And you obviously also can see the presence of vegetation. So then we can do the same thing as what you saw previously in the classification of the cubes, that we can start to look at the variations in temperature. We can start to understand the differences between the roofs, the different types of light roofs and dark roofs here. We can see the implications of different walls, and we can see the implication of different types of ground materials, so that we're getting large variations. Even if we just simplify the classification, that even within those, there's very large variations in temperature. And if we sort of just look at the order of those differences, as the order of 10 degrees over something that's been classified as being very similar, say impervious ground. So this isn't just one area of London. We're not, looking at multiple cities or across a city. So there are lots of corrections that need to be done, but I want to think about what's important for material, and with that, it becomes important to think about emissivity corrections. And for that, then we need to have a spectral library or information about materials. So we need to know something about we either need to know what are the materials that are present, so we need to have some way of actually identifying the materials. So remote sensing is very good for that if you have the right spectral signature. Or we need the alternative, we need to know what is the emissivity, because we need to correct that, because we've got our brightness temperature, but we need to understand what the differences in emissivities might be. So this is looking at with respect to reflectance and emissivity. This is, bricks. So you can see the variability just for bricks. And here we've only got 5 types of bricks. I am certain if we walked from here to the railway station, you would count way more than 5 different types of brick. So just, the order of magnitude of what the nature of the problem is, roofing, shingles, etc. So this work was done actually with Martin Worcester and one of my PhD students, Simona Coathouse at the time, and this was done with all the different building materials brought into a lab situation with lights and controlled measurements. Now, there's a PhD student at Forth, so same group as Maria's from, Gianni Laxarakis, who is doing spectral measurements. So what he's doing is, again, he's taken literally thousands and thousands of measurements, but that's still, he cannot cover all of one city. And that, so it gives you the sense of the order of the magnitude of what the problem is, of both the emissivity, being able to recognize materials, but also to assign a parameter. And that what he is able to do, though, is do these observations with very high spectral resolution or wavelength resolution, and that's going to make it usable with a really wide range of satellite products going forward, because he can assign those or align them to different satellites. So I want to move from materials to think about, so we've just been worrying about the buildings and their materials, but we haven't taken account of us yet. And so now we need to think about what we're going to do and try and think about some of the implications of that. And one of the things that is important, so we heard this morning about the energy balance in terms of radiation. Sorry. So in terms, okay, it's not as bad as it looks, I hope. Okay, so we have the building that energy balance. So we heard a lot about evaporation. We heard about turbulent, well, sensible heat flux, latent heat flux, and storage heat flux. There it was the ground flux when we spoke about evaporation. In the urban environment, we tend to talk about storage heat flux. It's this, we have the ground obviously still, but we also have the buildings that are heating up and cooling down. We have the buildings. So if we look at this unoccupied building case initially, so imagine that a building's just been built, but we haven't put anything in it and we're not using that, there's no electricity, no water. It's just basically sitting there like a lump of rock, but it's heating up and cooling down like a tree. So the building itself is changing the energy balance. It's changing the radiation balance. You would actually see an urban heat island effect purely from the geometry of the building and its materials, with nothing to do. I mean, obviously people built the building, but if they all went away, there would still be an urban heat island effect. Then we have the fact that, in this room, this part of the room especially, is very hot. I mean, we've got lights, we've got the presence of us, we've got these computers and things like that. So there is a lot of energy that we're going to be, we're obviously modifying the energy balance of this room, but we're also having an implication on other materials and the external walls. So those we also need to take account for. So that's going to modify. So we have the energy consumption, and then we're changing the storage heat flux, and that's going to impact the radiation balance. So we need to account for the energy that's being used, but also those activities. We're all here, you guys are here Monday to Friday, and then you're going to disappear. And, depending on, if you work in the UK, you get up probably later than if you work in the US and things like that. So we have social cultural norms about when we do things, and there are certain times where we take holidays, and we can pick that up in terms of how that influences the energy exchanges. So people's activities matter. And we also make decisions about buildings and when we use heating and cooling. So we have the building materials and where the windows are located. So we have all these different decisions about the buildings. They're going to influence how that energy inside the building may actually get to the outside. So here I'm thinking about everything with the perspective of outside the building right now, not the inside of the building, although it obviously modifies the temperature. Those decisions then of what the energy exchanges of what the building's built of will change then how much energy is getting to the outside, and therefore what are we going to actually detect. So we have those cases we just looked at. We took the same building, we just modified a whole series of different parameters. But if we go across the city, you're going to see the orange is non-residential, the blue is residential areas that you see that you have, in this case is Berlin, that you have pockets of areas that are very different in terms of, is it predominantly residential or non-residential? So, we tend to go away from workplaces during the week and go spend more time in residential areas. So we modify where our energy is used. But we look at these different areas, we will see that we have different land use, so residential, non-residential breakdown, but also we also have differences in terms of how areas are heated, when buildings were built, how those different aspects of the city are operating, so that there are some decisions that you can make as an individual, and then there are other things that are being made at a neighborhood scale and therefore have an implication. That means that if you go from the center of the city to the outside, you're going to see variations in building volumes, you're going to see variations in building area fraction, the release of anthropogenic heat, variations and population density. Basically, all of those things generally drop down. This is again in Berlin, and things like vegetation increases as you go to the outside of the city. So there's not one dramatic change, that's slowly changing across the city. And so that means that you can't just assume that the neighborhood in the city looks like one thing. You've got to be considering these differences. Then we have our individual activities, and each one of these lines, so this is an example of 200 people, these are the same 200 people that have been simulated. They're using time use surveys, so they're quite realistic people, and that you can see that what they do on the weekday and the weekend are different. The grey is that they're at home. You can see clearly there are different times that people are spending at different places, when those activities occur. So, and that again gets repeated thousands or millions of times, and that those things all combine to have implications for anthropogenic heat flux, which is going to, so that's the amount of energy that's actually emitted to the outdoor environment, and we need to also take that into account. So we not only have the materials, the building form, we have people's activities influencing what we're going to see with those satellites. So in the end, we have incredible amount going on in the city. We have all our different activities. We have the different land surfaces. We have the fact that the buildings vary across the city. We have our activities, and then we have the fact that we move, and that as we do that, we're also having an implications for that in terms of surface temperatures. And if you look closely at that movie before, you would have actually, if you watched it, you would have actually seen cars moving along the streets as well. So, that is showing up in your, satellite or other land surface temperature source of data. So we end up with these really mixed patterns of residential population, workplace population, thinking about, where are certain types of activities, where is hospitality, where are the restaurants, where is that cooking going on, things like that. Where are the large shops? And those are areas that people go to, and all of those are going to have different signatures that we need to consider. So I want to turn now to thinking about application. So my guess is there's not one person in the room that hadn't heard about the urban heat. Has anyone not heard of the urban heat island before they came to this meeting? So we'll start quickly with that, because this is probably the most well-known urban thermal property, and that we need to understand what it is. So there's 4 types of urban heat island. There's 2 atmospheric ones, the urban boundary layer, which is sort of above the roughness, so high above in the atmosphere. It's sort of the layer that is has air pollution or changes every day. The urban canopy layer, this is us walking around within the buildings and things like that. So think of the urban canopy layer. If you see buildings or trees, whatever the tallest thing is, that's the top of the urban canopy layer, and that's the air temperature that we're interested in. We have a surface temperature, so this is probably the one in terms of satellites that we're interested in. So we have surface temperature, urban and rural, but there are also cases of looking at the ground and subsurface below that. So if we're from a meteorological perspective trying to think about either the canopy layer urban heat island, that means that we're likely to be interested in air temperatures. So that means that we are interested in screen level temperature. So you can think of that as being 1 to 2 meters above ground level. And so that we're explicitly saying it's between the roughness elements, between these buildings and that trees, that is the air temperature, and that's what we're walking around and experience. And we need to get the urban measurement, and we need a similar measurement in the rural environment. For the surface one, this is more challenging, because now we've got to figure out, well, where actually is that surface? Because again, I've gone back to the simplified cubes, but remember, these are characters, they're much more complex than that. So we've got to really consider that. But we either need to think about the complete surface, so all the different facets and orientations, or the plan view, where we're just looking down, so we've lost all the walls and things like that. So comparing the urban canopy layer and surface urban heat island, so we have the black line here during the daytime, so we're just looking at a spatial variation in temperature. The black line is the surface temperature, and the red line is the air temperature. And so what we see is that the black line is much more variable and is higher during the daytime. And at night, what we see is that they're more similar, again, the air temperature is sort of more similar to the surface temperature, but we see greater variability in the surface temperature, obviously, because we're dependent on all of those materials and facets, whereas the air temperature, we get some mixing. And obviously, if we look closely at any particular place, we can sort of understand where we're getting those variations from, in terms of from the roof, from the different materials, and the difference between day and night. Obviously, at the roof, what we've got is that the roof is cooling more rapidly at night, but it also is going to heat up more rapidly during the day. In terms of actually thinking traditionally about the urban heat island, then we've got to think about what is the difference between the sort of a city area, so sort of we're after one number rather than spatial variation. Then what we would be looking at is, how does that sort of urban area compare to, say, the surrounding rural area? But again, that we see even at the sort of Corson scale that we're missing the we're getting spatial variability, but understanding exactly where the rural area is important. But we're not detecting any of those details about what's causing that temperature to be variable. So just to look at that surface temperature, though, the difference between the plan view, so just looking at the top of the buildings and the ground, and the complete view, that you can see there's a very large difference in temperature. And so, if you're interested in something that is the roof temperature and the ground temperature, or giving a result for that, that is different than taking into account all the different facets. So again, being critical to make certain that you give that information. We need to think about that in terms of the materials that buildings are made out of, and also their sky view factors. And that we can look then to get spatial variations of that between day and night, and relate those to air temperature. For, say, numerical weather prediction may be interested in this, whereas we get a very different result if we were looking at the surface temperature from, this case, ecostress. Just to finish off briefly then with numerical weather prediction, we're looking at, so in the UK, your weather forecast from the Met Office was done at 1.5 kilometres. It's embedded in a global weather forecast model, but in some areas we can do, for London, there's sort of a research model that runs at 300 metres, and we've been doing with the Met Office this very high resolution 100 metre model, also with Chris Merchant, and so the land surface model that's in the unified model of the Met Office model is 2 tiles. So the city isn't as sophisticated as a canyon. There is a roof and a street that have different properties, and then there's vegetation, etc. What we want to look at is this slide. The second column is the modeled, the 100 metre resolution modelling. On the first column, we have MODIS land surface temperature and Landsat temperature. We do a difference. In an ideal world, you would not be able to see anything in the third column. You clearly can. This has been very, very useful work, because we found lots of issues using remote sensing. We're trying to look at LST. We were trying to look at it in an urban environment, but we found out lots of different things about, that vegetation wasn't being represented, or there were soil moisture issues. So there are a lot of benefits of looking at LST and comparing them that are not necessarily getting to the point of actually comparing the land surface temperature. So we're looking here at the MODIS and the Landsat image. This is the same image. So the furthest is looking at high resolution in London and trying to understand what the implications are of the view angle and what we're seeing in the satellite here. We've got, these all have the same properties, and this is now simulating using DART what the satellites are seeing. And thinking about, if you look at the nadir, so at 11 a.m. and at 2 p.m. and then at 2 off zenith, angle, off nadir zenith angles, and then trying to think about what is the implications of the satellite view, what's on the surface, and what is actually being seen in terms of the final satellite or sensor surface temperature. So you can see that the Landsat field of view is very narrow relative to MODIS, but you can have very strong contrast in temperature. So the order, depending on the exact day that you're looking at this and the angle of it, that you can have temperature differences of the order of 6 to 7 degrees. If we start to then take that and think about what are we actually seeing on the ground, so wall, ground, and roof, and look at the variations of that in terms of the level of detail. So level of detail 0 is our random cubes, level of detail 1 are flat roofs, and level of detail 2 is got sort of more realistic roofs. You can see then that as we go across, then the variation in the temperature is large in terms of what the implications are as we change that, and that has implications. So even going from flat roofs to realistically shaped roofs is having an impact. We can come back and look at trying to understand what might be going on with the Met Office modelling, and that we can see that there are differences, that they are related to land cover fractions, and basically there's lots of research opportunities here for all of us going forward. So just a couple of very brief examples now, again related to applications in numerical weather prediction. One is using those surface temperatures, so again back in London, so it's very high resolution modelling, and starting to think about the next generation of weather forecast models that actually can predict so you saw that the Mauritius model had 2 flat surfaces, and those are the city. The next generation will try to actually take into account that changing building geometry. So we actually need to be evaluating this, and this is work done also with Meg Stratton and SMWF. So what we're doing is evaluating a high resolution, vertically varying temperature model, radiation model, shortwave and long-wave radiation. I'm just showing long-wave radiation here. So we can pick up the walls and the roof. You'll get the changing geometry. You won't get the orientation of the wall, and you're assuming the buildings are randomly located. And so we've done this for a whole series of different cities, but this is again in central London. And we can see that although the model tells us a lot more information about the variability of those surface temperatures, it is reasonably fast. DART model is 10 to the 9 times slower than your sort of typical weather forecast for one grid. You can see why we don't use DART. I mean, you can see why you can't have these details and get that information. But if we can start to bring up some of these details, that you get sort of a reasonably good performance with not too much computational cost. And then using the same observations, but dropping down a scale to think about building design. So we think back to, if you're going to stop emitting so much energy outside, saving energy use, then building design is really important. So you would like the building designers to be taking into account those long-wave radiation considerations, those surface temperatures, and thinking about those. It makes a really big difference if we can improve. They do a very good job of modelling the individual buildings, but if you don't take into account the neighbourhood, then it has a very big effect, and therefore the impact may be large. So there are lots of challenges in the urban environment. That's really great because that's lots of research opportunities, lots of PhDs, lots of postdocs, lots of research grants, etc. It's really important to think about the implications of the assumptions you're going to make. You're going to have to make assumptions. So it's not give up. It's thinking about, okay, what are the things I'm going to simplify? What are the things I've not considered? And think about that. And then there are lots of applications. I mean, I'm certain each of you could have come up with 10, 100 other applications that are really important in the urban environment. And they are really, really critical because we all make decisions as an individual, but those decisions have implications for the environment, they have implications for health, they have economic implications, they have social implications, they have justice implications, they have planning on transport implications. So we've got to think about how are those decisions made at the microscale? Can we make certain that decisions made at microscale, they have a reasonably good idea about what's happening at that neighborhood, and then how does that fit in to the neighborhood, into the city, and into the region? And that if we find problems, we can help, and as we improve things and find solutions, we also need to check that they were actually beneficial. We don't just assume that was good. Unfortunately, green buildings that were built, designed with London Heathrow meteorology put into central London, it doesn't work that way, and retrofitted very, very expensively and not having the environmental benefit. So lots of very important things bringing these together. Thank you.
Any questions from students?
Like I got the first one. Yeah, thank you very much for your presentation. One of your slides says like the orientation of the buildings do have impact on the temperature. Like I see the building towards east, like two buildings to west, like a 5 degrees sometimes difference. And this temperature was measured during the daytime. My question is, do you see the similar pattern during nighttime?
Yes, you will see that, and if you go back to that video, which you will actually see the rate that it's cooling. So the roofs will cool and become isothermal faster than the walls because they see more of the sky. But there will be, straight after sunset, there will be strong contrast, and then by sort of just before sunrise, the spatial variation will be least. But yes, there will still be large variations at night. Yeah.
So the first was to do the presentation. I work in validation, right? And the urban bio that's been previously collected in the 6 station knowledge, but now that satellites like LSTM and so on are now capable of resolving stuff with urban landscapes, we now have to think about how do we assure being see the satellites in these regions. It's very difficult areas about it because practically every service, as you showed, has a unique signature. In your opinion, I guess I have 2 questions. First one, how would the research that you've done and are continuing to do, how could you leverage for assuring the quality of satellite data? And secondly, if, for instance, a city like London was this, if you have everything like half of your presentation, you had a thermal imaging camera, how many of those do you think would be necessary to validate a city like London, for instance? And would the validation results of a city like London help you want to determine whether a city like, whether observations over another city like Paris or New Delhi would be equally as accurate?
Okay, so first question about sort of the complication of the materials, and I would treat that as sort of like an emissivity and recognizing the materials question. So I think the spectral library work, for example, that I showed you from Forth, that is really critical. Yes, you need thousands, but it's not infinite. And we know also how retrofitting is occurring and what materials are used. If we take that, a lot of that work was done in Heraclean. So let's say that 6,000 spectra was of the order of enough. And then we go to the next city that you need another X thousand. That relatively quickly, and this is Jonas Workes, he is actually testing that to see basically how much information do I need to be able to identify all the materials and therefore say, okay, I know what's there, and therefore, what would be the emissivity. So I think that work is doable. It's going to need a lot of people. He's doing this. He started in Heraclean. We're doing work also in Berlin, Paris, and Bristol. Obviously, Heraclean is tiny compared to London or Berlin or Paris, but you'll also suspect that there will be more consistency. There will be consistency in one place versus another, but as we go to global south and things like that, there's going to be lots of materials. But I think that is actually an achievable action, but it's going to need a lot of people on the ground to do that. In terms of your second question was, actually, better tell me, there was three, so I know. The modelling. Okay, so what we're trying to basically figure that out in terms of the thermal cameras. So we had 6 thermal cameras looking in a lot of detail. Some of the analysis work that I showed you at the end with Morrison, we can start to see that some of the simplifications we're making, it's not too bad. Again, that's going to probably really depend on what materials are there. It seems that the atmospheric corrections close to the buildings is really quite important and can be very large. How many? I think it's the geometries. I mean, we're trying to sort of look at the dark modelling is way too complex to consider doing large areas. We've done sort of several large areas of London, but 2 kilometres take literally days to do one day, so it's not practical. So we're looking at sort of faster models and what the implications of that. So spending quite a bit of time working with the building engineers, the energy plus people that just think about, can we get those correct and what are the implications of that? Interesting thing that's happening there is the materials are important, but people's activity and household structure there is turning out to be really important, and that's going to be more challenging. But it does suggest that we can look at archetypes and think about how those are arranged. And what was the last question?
You've answered all of them.
Okay.
Thank you very much.
Last question.
So my question is rather different to the previous one, but they are strongly correlated. In the era where we hope we're going to have increasing social justice so that a large part of the poor population who live in urban areas no longer have to live in substandard. Your studies so far, do they inform you as to how it might be possible to detect where there is no insulation in the roofs?
So we're looking at a slightly different, we're thinking about that, but we're thinking about it in a slightly different way at the moment. We're thinking about if you start off with buildings that have, yes, with thermal cameras, and we can definitely pick that up. We could definitely see that. What we're trying to think about in terms of that is if some people can afford to retrofit and others can't, what are the implications for those people that start to retrofit? So, for example, you get a benefit from the heat release in the winter, and if everyone seals their heating into their building, those people don't need to pay so much for heating, but the people that can't afford to retrofit are going to need to pay more for heating because they're not getting that anthropogenic heat releases anymore. And so we're trying to think about that and what the implications are for building materials. You can then detect, obviously, relatively easily, thermally, where that's happening, where the heat losses are. And then going back to the emissivity information, you can improve then what the actual surface temperature differences are, rather so correct for those. And we've also been thinking about other like atmospheric corrections for those.
If I could ask a quick follow-up, which is that one of the things, of course, one would like to be able to do is to map an entire city, and the only way at the moment practical way of doing that is with satellite data. But the difficulties seem to be enormous for being able to detect those buildings which actually have inadequate insulation.
Yes, I mean, you definitely in the end, everything has to be probabilistic and for the modelling, so we actually can model every single building in London. We know probabilistically what its age is, what its dimensions are. We don't know the absolute truth, but we know what from sort of various data sources. In this area, there's this type of building. This is the age distribution. There's something about the economic, social justice. There's a bunch of information, so we can have a look and think of what the implications of it are. We're not, we don't know exactly where any individual really lives or the exact building. One of the things that we can then do is look at what are the implications if they had better or poorer building materials and things like that.
Thank you.